Right. You're just in time for the start of the race, okay? Just in time. Here we go. We've got 299,792 kilometers per second there, and we've got absolute there. All right. We're going to race. Let's race to Mars. All right. Take about 13 minutes. Let's see how we go. All right, you two, on your marks, get set, go. Back here. All right. So, absolute's already gone, yeah? It's gone. But everything's to scale, remember, just the distance, not the planets. Mercury's not that big, it's not that smudged. But takes 3 minutes to get to Mercury, so it gives us time to talk. Well, absolute light's already gone. So if I probably click this at about 30 seconds at the beginning, so we're looking at when it gets to about 3 minutes and 30 seconds, that light will have arrived, the sun's light will have arrived from Mercury. So still a ways to go. Now, the crazy thing is about all this, right, is they tell us that if you were on planet Earth and you were looking towards the sun, if the sun were off and if someone turned it on from off, you still wouldn't see it for 8 minutes and 20 seconds. So your eyesight, even though you're looking straight at the sun, you're not going to see it for 8 minutes and 20 seconds. It's going to actually come, it's like the propagation of the wave needs to propagate over and over until light is done, and then it repropagates. It's a propagation event. And at 8 minutes and 20 seconds, that's anyway, don't get too distracted or we are going to miss. So we're looking at 2 minutes and 7. So minus 30 seconds, it's 1.5. So we're halfway there. All right, I jumped the gun earlier. So this is like traveling from the sun just to Mercury, right? We're still hanging about here. Yeah, there's a couple of other things. So when you're looking through a telescope, if you're on Earth and you're looking at, say, at Jupiter or Saturn, which by the way we can see with the naked eye, all right? So if you're on Earth looking at the rings of Saturn, you're not actually seeing Saturn where it is. You're seeing it where it was, right? Because it takes light 1 hour and 20 to reach Saturn from the sun. It takes 1 hour and 20 for it to reach the sun, and then about another hour 10 for that reflection, the light, to come back to the telescope. So basically, you're looking at a 2.5 hour. When you're looking at Saturn, you're looking at Saturn where it was 2.5 hours ago with a telescope. Do you know that? And without a telescope, in fact. So when you look up, oh, that's Saturn there. No, Saturn's already gone, right? Because that's 299,000. Oh, at 3:30, we've just reached Mercury, look. So in the time that I've been speaking, the sun has travelled from the sun to Mercury. So on its way to Venus. So anybody, even somebody right now on Venus, like even though the sun has arrived at Mercury, like this is a propagation, the waves, okay? Because it's propagated. It's a propagated wave that comes out. So it's probably going to be about here now, right? So people on Venus, because there's quite a big colony of people on Venus, if they were looking towards Mercury right now, they wouldn't even see a shadow. They wouldn't even see a shadow of Mercury over the sun because they can't see the sun yet. It's a weird one, isn't it, right? So yeah, and anybody on Earth, if we're all looking, what's going on? When? Like, can't see a thing, even though the wave is propagating, it's coming. So that would be 6:20, so we're looking at 5:50, and we're still, oh God, we're only on 4:40. So we've still got ways to go, but light is slowly getting there. Just takes a while, that's all. What else is there about this absurdity? Now, that's what I was going to talk about. Good job I remembered. Shouldn't there be an easy way? Because according to this science, because it's finite, it actually travels. Put that there by now. Just got to check. I don't want to miss. I don't want to get snowed under afterwards. That's five. So we're on 5 minutes. So we've got another at 6:20. Yeah, 5. Say we're on now 5:10. But yeah, all right. About another minute and a bit. With the laser, because light travels. Somebody's on Earth, right? And you point a laser at Mars, right? It's going to take 4 minutes and 40 seconds for this laser to reach Mars. Now, let's say you got halfway, somebody got halfway, and Mum called them in for cornflakes or for dinner or something, and they drop the laser. It cuts off there, but this beam still carries on its own. Right, hang on. Venus, so we're at 5:20, where are we? And all aboard we are. Anyway, so light has just reached. At the time I've been talking, this is height from the sun. This is what it's doing. This is where it's at right now, okay? Still got another 2 minutes before it gets to Earth. So this beam, kid running for dinner, right? Drop the laser, cuts the beam, but the beam carries on. Like, so you've got a 1 minute beam, and it will get to Mars, and people will see, what will they see, I wonder? They'll see the beam of light. It will hit them in the eyes, they're going, and then poof, it will disappear because it was only a 1 minute beam. But if the guy had held it the whole time, when the beam finally reaches, right, and then he's called for dinner, and he drops the laser, just so he drops the laser, nothing's going to happen to this light because it's already en route. Okay, so whoever's watching this beam going, oh God, I can see somebody pointing the laser pointer from Earth again, right? And it will last 4 minutes and 40 seconds because the guy threw it down as soon as he was calling for dinner. So we've got 7, so we've still got another a minute before the light reaches Earth. We're about there now. So if this is the case, right, because it is said that it is one of his favourite hobbies is who's that? There's somebody who he likes to hold his laser for about a minute and then let go of the button, and he knows that there's a. If this is the case, right, should that not be easy enough to prove, right? Because with mirrors, we're looking down onto. I just want to make sure we don't miss. I hate to miss Earth getting the light. We're on 8:27 now, but we've got to add the 30 seconds that I was talking at the beginning before the race. So we're coming up to 8:40. Now we'll be here now. But the light's here, but you're still not going to see anything. Nobody knows yet. And then, when the time is right, which I think we can call it now, 8:50 minus that, push, there is, right. Right, so now we've got another 4:40 before the light from the sun reaches Mars, okay? So now we're looking down, right? Let's say something the size of a sports field, right? We've got the track that goes around the outside, 400 meter track. Right, now, if you put mirrors, like really good sized mirrors on each corner, right? Right here, you've got 400 meters, haven't you? It'll be a little bit more because we're on the outside and the 400 meters is in there. So you're probably looking at, you might be able to squeeze 5 500 meters out of a track, right? 125, 125. That side might be a little bit shorter. Anyway, look, call it 400. So you get an entry point for a laser beam, like say here, right? And you fire it, like you know how they do, you can make a little hole in the mirror, but when the beam comes, because of the way the mirror is over the hole, so it doesn't see the hole, and it's just a perfect bounce. And it bounces onto that one, bounces onto that one, and bounces onto that one, and then back from the starting point, but it doesn't know it's the starting point, it's just bang, another mirror, and bang. And so what we have, with just 4 mirrors positioned in the right place, just check the, how Earth is going. So, oh, God, look, I missed it. Oh no, sorry, Earth has got it, it's Mars we're on about now. Oh no, sorry, I jumped the gun a bit there. Sorry Mars, you've still got another minute and a bit, nearly 2 in fact. So now we've got the laser, fired the beam through this mirror with a hole, but when the laser comes it doesn't know it's a hole because it's covered up, it's perfectly structured this way. And we've got a beam of light. Now if it travels like they say it does, you should be able to take that laser away and the beam of light will carry on. If they leave it on for a minute, I mean, I don't know how it's supposed to work, because the way I see it, light is absolute. So as soon as you turn that laser off, the light's going to stop. You don't turn the laser off and it cuts it off and it's its tail and it just follows the front of the light and it just keeps going and keeps going and keeps going. It's an absurdity, but that is the finite speed of light at 299,792 kilometers per second. It's hard to prove whether it is 299 or it's absolute, right? It's one of those things where we are that we're never going to get the range, but this will in fact prove if it will carry on its own, right? So these are the claims being made. So it's horseradish, right? But surely bouncing a laser off of 4 mirrors in a sports track, you will find out, won't you? Because it's going to go 400 meters at a time, 500 meters at a time. Keep that finger pressed for 5 minutes. You've got yourself a good 5-minute beam of light going. And then when you let go of the laser, so we're on 30, okay, we reached Mars. Boom, right? Now, for it to carry on to Jupiter, it's got another half an hour, right? Another half an hour to get to Jupiter. And then, so that's 43 minutes. And then Saturn, it's an hour 20. Uranus, 2 hours 40. Neptune, 4:10. And finally, Pluto is still a planet, 5.5 hours, right? Now, all we have to do is bounce off of 4 mirrors to see if it really does travel on its own. And this is the same as this craziness, as crazy as it sounds, to wait 8 minutes and 20 seconds to see light and not be able to see it even though you're looking at the source, right? Is if this suddenly turned off, you're going to have exactly the same again as waiting for the light, as waiting for the darkness. Because obviously this is the tail end of that beam of light now. So, right, these things are ridiculous, right? This is the absurdity, one of the biggest absurdities ever known to man, I'd say. And for so many people to have fallen for it. But now look, this is what is being said, right? All that time, you can look up at the night sky, right? And you can see when all the planets, the first planets closest to us are in alignment. So you've got, not with Mars, Mercury, say Venus, right? When it does that retrograde thing, it's just on that opposite side and we come around in our orbit, and it's in front of us, right? So you have Venus, Mars, Jupiter, and Saturn. You see the four of them. So what is that, right? You're not seeing them as they are. You're seeing them as they were, because they would all really, in theory, have all shifted slightly. But no. So what is it about this that seems logical, right? 299,792 kilometers per second. 3 minutes for light to get to Mercury. Absolute, which is so obvious, right? Sun. It's got the diameter of 1,390,000. I know I keep going on about it, but you need to hear it again and again. At the speed of light, at 299,792 kilometers every second, it takes the sun 4.6 seconds to radiate light that distance, and another 4.6 seconds, and another 4, which is why we saw it going so slowly up there, because it's a case of 4.6 seconds, 4.6 seconds, 4.6 seconds, 4.6 seconds, 4.6. Well, yeah, on its way to Earth. Now, it's ridiculous. So, in my head, I've been working some way to try and get an angle, a foot in the door for this measuring. This has got to be it. This has got to be it. 4 mirrors. Bounce that light off. Get it well revved up. Keep that finger on that button. Make sure you've got a good beam of light that's, you know, really going, because it will be within 1 minute. I mean, jeez. Alexa, what's 299,792 multiplied by 60?
299,792 times 60 is 17,987,520.
17 million, right? 17 million seconds. No, 17 million kilometers, sorry. That's in 60 seconds, right? 17 point something million kilometers in 60 seconds. So you keep that finger on there, all right? 1 minute. So you'll have a beam of light that's 17 million kilometers long. And then as soon as you let go of the laser, or somebody just snaps the trapdoor shut on the light, what do you think is going to happen? Think it's going to carry on? Yeah, no, the door's shut, the laser's away. Is the light still going around the track? Yeah, still going. Do you really think that's going to happen? No, it's not. No. As soon as that trap door is shut, it doesn't matter how long you've been shining the beam of light, it stops. Dead. Because light is absolute. It would stop dead. No source, no light. And should we do, I think we're going to be smoky enough. Right, let's have a look. Let's see if we can do it here, all right? I know we can't. I'm just having a bit of fun, but because that's what we do. Where's my laser? This is not a good time to misplace the lasers, because that light is on its way, and if we're not at the bus stop when it gets it up. Oh no, sorry, that's the finite light that keeps it mixed up. So what we have, see, the table's moved since I first set it up. So we've got one laser, 5 mirrors. Let's turn this light off. Well, I'm going to bring my atmosphere enhancer in, because it's good to let me get a bit closer and zoom in. Actually, there's no need to zoom in, so you can see where that laser's coming from. So we've got a bounce to there. And this one bounces onto there. Right. And that one bounces onto there. Oh look, see, that's what I mean. Boom, no source, no light. And then this one, where you bounce it onto there. And this is now where you're going to need some kind of a method to have the light that is shining into the circuit hidden, so that, because I'm now with these, doesn't matter what I do, I'm going to end up blocking that, because I'm going to have to move this mirror, see? But surely this can be done easily, right? This can be done. 4 mirrors on a racetrack with a good laser. Fire that laser, right? So I'll go there. No, so you can just shoot that off and have some fun. Hang on, I'm just going to go get the atmosphere enhancer. To get a bit of smoke going, you know what I mean? Right, shut that door. So, with the 299,792 kilometers per second, if there was 400 meters between each of those, it would, if you got it to go quite a few times round, you'd easily be able to work out if it really is finite or not, wouldn't you? That's probably one of the better ways that I can think of proving something like this. Maybe suggest it to them. They've got all that money, haven't they? And if they can get to the moon in 1969, I'm sure they can set up a few mirrors that rebounces the beam of light back onto the first mirror, so that it just keeps on going, isn't it? That looks cool. Just getting a bit of smoke going, that's all. There we go. So what do you reckon then? Because these are easy to move out. Right. See, how hard would it be? Look. So ready, we can, with these, I can take this one up here and make it bounce off of this one. Right, and then get this one to bounce off of that one there, which is on the table. Right. How hard would it be to get a good little circuit going? And then we could I mean, we'll try it here. We'll see how far we can go. Where are we now? We're bouncing up to there. So I need, I'll probably put the big white mirror up there. To catch that beam of light. Oh, right, so turn this one a bit more. What's that? What was that? That was fucking what's her name, wasn't it? Oh, I know what it is. That's all good. Right, so there we have it. Look, so we've got a multi-system of lights going. There we go. If I get rid of the source down here, my hand's coming down here. All gone. The only one we see is the original laser that's coming from the laser. And look how many strands of light it is. Look. So that laser is broken into. Look, here it comes. You can see it. Oh, it's hard to see. There you go. Look. All those strands, whether it's from a smudge on the mirror. So that's going over us now. But see how many. Going through it. Through Statton's rings. Oh, that was fun. Alright. And if we go this side, he's looking at it from this angle. So they can easily set up. And now I'm going to cut the source, and this would happen. Look. Gone. Gone. So if it really does travel at this finite speed of 299,792 kilometers, it should be quite simple to do that with mirrors. I mean, they are brains, aren't they? So, why not do it? Don't you think it would be an interesting thing? Get those mirrors going. Because otherwise, I mean, we don't have a single equation that proves that they ever work the speed of light out coming from the sun or anywhere else. There is never a concrete equation that says, right, this represents 50 k's an hour and I'm bouncing off of this mirror and this mirror, which won't accelerate because it's just a mirror, isn't it? So whether it goes at 8 k's or not, it just really is not going to make much difference to any reading that they get. Spinning the mirrors and everything, because it's an absurdity. So there you have it. How much would that cost? Some nice big mirrors. I mean, they make massive mirrors for the James Webb Space Telescope. 4 of those would probably do it, because it's in sections, isn't it? Bounce the light around the sports arena, fill it up, get the crowds in there, they love it. We're going to show you, we're going to shut off the beam, and it's going to carry on travelling. Just keep on going on its own. No source needed. There you go. Try that one at home. Or don't try that one at home. Let the professionals do it. All right. Some more absurdities soon.